Hello, everybody. My name is Amit, and I'm going to talk about our Cloudinary's journey from data warehouse into data lake and what we learned from our journey. So a bit about our agenda today. We're going to talk about the entire flow we had to go through until we felt ready to productionize our migration, ingestion, compaction, maintenance on our Iceberg tables, monitoring, and the best part, benchmarks we did once we finished the entire migration. So a bit about me. I've been working at Cloudinary for the past 3 years almost. Open source contributor in a few Node.js projects, not entirely the data world. Hoping to create my first PR for Apache Iceberg, working on some issues there on branching. So I hope by at the end of the session, you'll be better dressed and equipped for this icy journey and avoid frostbites. So let's talk a bit about Cloudinary. So Cloudinary is a platform for delivering, optimizing, and managing your digital assets. Essentially, what we do is when a user requests an image or a video, we identify the browser and device that's requesting that asset, and in real time optimize it to deliver it in the best quality and the format that the user requested it. So we have a lot of named brands using Cloudinary: Nintendo, Levi's, small companies. And if we try to convert it into numbers, we have around 10,000 customers, 2 million developers using our platform. We manage around 60 billion assets, and we serve around 30 petabytes of bandwidth every month. Now, if we convert that into analytic logs, we need to bill our customers and analyze them. We process around 10 to 20 terabytes of logs daily, 50 billion records, and it's around 7 to 14 gigabytes of data we need to process every minute. So why did we choose Apache Iceberg? We chose Apache Iceberg for a few reasons. We wanted to reduce our cost on our current data warehouse solution, which was Snowflake. Every year it grew and grew. We wanted capabilities like time travel. We wanted to implement new features for our customers on top of our data, and using the existing solutions, we're really binding to that single query engine. We wanted to utilize multiple query engines, Trino, and other query engines, and support according to our business use cases. And we wanted to hold more data. Storing data on data warehouses is very costly, and the more you store, the more you pay. So we wanted to utilize like AWS S3. Another reason we chose Apache Iceberg, if you look at OSS Insights, we were looking for solutions that were adopted by the community. If you look at Delta, you see a huge circle, which is Databricks, which is the main maintainer of the project. And if you look at Apache Iceberg, you'll see that there's no one organization behind it, but it's contributed by a lot of organizations, which is really awesome. And you can see how much it's a community project. So this is our previous architecture at Cloudinary. So like I said, we serve images to our customers that generates logs from our CDN providers, which upload those logs into our buckets on S3. We then use Spark to process those logs. Once they're processed, we save them again on S3 in a unified format after we aggregated them. And after that, it's being uploaded by Snowflake, Snowpipe, into Snowflake, and then queried by all our different teams. Now, as you can see here, we have already one issue where we have 2 copies of our data. So we have on S3, which is sometimes being queried by analytics teams and security teams with Athena. And we have other teams using that same copy of the data on Snowflake. So that already doubled our storage costs. So by the end of this session, I'll show you how we reduced our storage cost by 25%. We retained 6 times more data. We reduced our query cost by 25 to 40%. We now work with only a single copy of our data. And query execution time was reduced between 30 to 50%, which is really awesome. So before you get ready for your journey and you chose an open table format, you need to look at what's really important. Select the tables you want to migrate. Pick from those tables what are the mission-critical queries that you are going to benchmark, how much a query costs you in runtime and money, and of course, who are the users that are actually accessing those tables and what tools do they use? Do they use only Snowflake? Do they use some BI tools? Because you'll need that info to understand if the platform you chose or the open table format you chose or file format are working with those platforms. So let's begin our journey. We're going to start ingesting data. So the new architecture at Cloudinary is we still get our data from CDN. They still put it on S3. But now we don't upload it anywhere. We just process those raw logs, and we save them on S3 with Amazon Glue as our catalog. We use DynamoDB to handle locks, so we don't process the same files again. And we chose Parquet as our file format. We decided on different file sizes for each table, partitioning, and does the table need to be sorted, or it can be just bin packed without any sorting. So why is file format a really important issue when you're choosing to move to open table format? So like I said, you need to understand who your users are and what platforms or what solutions are they using to query the data. If you look here, Athena, Spark, and Trino support Avro, RC, and Parquet. But if you're moving to Apache Iceberg, so Snowflake currently only supports Parquet files. So that was an important decision since we have a lot of teams that are still using Snowflake to query those tables. Another consideration is compression. So at Cloudinary, we try to benchmark different compression solutions. So if you look at it, we found that Z standard is better in compression, but there's a little price to pay when you do compress the files. But if you pick Snappy, then the compression is less, it's less compressed the data, but it's accessed faster. Now, since we process 10 to 20 terabytes of data on a single table, we wanted the compression to be better, so we chose Z standard. A few configurations we use to optimize our ingestion. You have table configurations, which is Apache Iceberg configurations you set on the table, like target file size, write distribution mode, compaction, compression, like I said, Z standard, and how many versions of our metadata we want to store. And on the bottom, you have adaptive query execution, which is Spark configuration that's only supported from Spark 3 and up. And it handles the distribution of data between the nodes. So it handles, so you don't write too many small files, but you don't write too many big files, which is really important. So another consideration we went to when we're working with Apache Iceberg is how are we going to update our tables when we ingest. Some tables update columns and do enrichments on the data. So Iceberg supports two mechanisms. One is merge on read, and one is copy on write. Merge on read is essentially saying if you updated a row in the table, don't modify the existing file, create a new file, write that modified row into the new file, and create another metadata file that just states which row was deleted in which file. So like it states, merge on read, it means it's more expensive. The more deletes you create on your table, the more metadata files it will need to read, and more when you run the queries, the more time it will need to prune the unnecessary rows from your existing table. And you can understand why it's really fast when you write. Now, copy on write is a lot more expensive when you're ingesting data, because essentially what it's doing is locating the files with the rows you updated and rewriting those files. So as you can see, data file 3 was just rewritten, and now it's data file 6, but you had to read the entire file and rewrite it. So if you do it on a lot of files at once, this process can be really, really expensive. Currently, the only query engine I know that supports copy on write is Spark. I know that other query engines don't currently support it, and I can understand why it's a really expensive process. So now we ingested our data, and we have data written on our S3 bucket, and we can query it. It's time to optimize it in the background using rewrite data files or compaction. So what do we do when we compact data with Apache Iceberg? So there's a few steps, and I'll walk you through them. One is the most simple one, what is compaction? We're just taking a few small files that are not the target file size we wanted. We're merging them together to get to the optimal file size, so we don't have too many files, small files, and then query time takes a lot longer. But now, if we created delete files, compaction can also solve that problem. The compaction process can take care of all the rows deleted from our files and remove them and compact them with other files. So it's a very important process. It's configurable. It's called delete file threshold if you're using Spark. And the default value is the highest number an integer can be, which is bad, because if you have a lot less deletes in your file, it won't be eligible for compaction. So you should look at that when you're running compaction. It can drastically improve your queries if you handle deletes. And the strategy you're using to bin pack your files. That's really also important. There are 3 supported strategies currently with Apache Iceberg. Bin pack, which is the most simple one. It doesn't require any shuffling of the data. It just scans the files that are eligible for compaction, and it just converts them into groups and merges them. It's really fast and really simple. Sorting is a medium operation. It takes your data and sorts it according to your columns you chose. It's a medium operation. It does require sorting. It does take more time, but you'll see the benefits of it soon. And Z-order does clustering on the data, and it's the most expensive operation. I won't dive into it because I never had a need for it, but it does help if you need to cluster similar data together. So how is the compaction architecture at Cloudinary currently? We're using 2 methods. One is using Airflow and Trino. The other is Spark. For our biggest tables, we're using Spark since we're ingesting around 14 gigabytes of data every minute. We need clusters that are always on and listening. And essentially what they're doing, they're querying Iceberg metadata tables. So Iceberg, when you write data into Iceberg, it has a lot of metadata tables that allow you to query what's going on with your data. So you have the snapshot table, partitions table, deletes, and files tables. And you can use that information to understand on specific snapshot how many files were written, how many rows you wrote into that snapshot, what was the size of the data written, and you can extract from that the average file size that currently is on your table and understand if compaction process needs to be done. You can even query deletes table, which tells you what's the status of current deletes on your table, and do you need to also include in the configuration set a delete parameter to catch those files. And we have Airflow that does it on a scheduled basis. And every time it finds a table that needs compaction, it will call Trino and tell what table and what to run on that table. So, like I promised, we did a benchmark at Cloudinary where we took the same table, the same week, and we tried 2 compaction strategies on that table. We did one time with bin pack, one time with sorted data. And what we did, we took our 4 most query-intensive processes that we run every hour in Cloudinary, and we tried to test and see what was the result. So on the one side, you see the data scanned per query, and the other side, you see the query time. And you'll see something happening there that when you use bin pack, almost always you scan twice the amount of data, and the query execution time is almost always takes 2 times more. And since that was the benchmark we did, we understood that for that table, we prefer sorting since it has so much data. And once you sort the data, your query execution time goes down by half, and it makes sense. You scan more data, you take more time your query execution time takes more. Now we finished ingestion and compaction, and now it's time to maintain the table. So usually this process on data warehouses is done for you, but now you decided to move to Apache Iceberg. It's time you maintain your own tables and metadata. So let's talk about it. So one procedure you have to do when you move to Iceberg is expire snapshots, which is essentially saying how far do you want to go back with time travel. So each commit, each time you write into Apache Iceberg table, you're essentially creating like a git commit. And that's a point in time where you can travel to. But that means you're referencing files which are still saved on your storage. So you need to decide how much time travel do you want to go back. And once that snapshot is not valid anymore, you want to delete the data and that snapshot. Too many snapshots can create a huge metadata files, which can affect query planning. Another process is, I like to call it as rewrite manifest, which is essentially compaction, but not for data files, but manifest files. So every time you write data, you create a new manifest, but essentially it's creating a lot of small manifests, and you can compact them together to actually optimize the manifest file sizes. And one thing we realized we didn't run it often enough. And when query planning took us around 12 seconds before we ran it, after we ran these procedures and starting adding them to our flow, we saw that query planning time was reduced to around 4 or 5 seconds. So this is really, really efficient to run it. Okay, and the last but not least, delete orphan files. So essentially, when some Trino cluster or Spark cluster runs a query, if it writes into your table and for some reason the process hit an exception and exploded, you wrote data into your storage that is not referenced by the table. So there's no reference to that file. And you essentially just have dead files that's nobody accessing them, and you're paying for it. As you can see in the graph on the right, so at Cloudinary, when we implemented this delete orphan file procedure with Spark, we erased around 100 terabytes of data. Now, if you convert it into money, which most companies understand, it's more than $2,000 a month that we would have spent on those files that are not accessible, but are there. So it's really important to run this procedure. Don't run it all the time, because it works like a garbage collector. It needs to cross-reference the files on S3, if you're using it, with your manifest files to understand which files are not referenced, and it can be very, very expensive. Take it from me, I ran it with a huge cluster, and I hit S3 throttling, which shut down production for a few minutes. Not recommended. And this is our maintenance architecture now at Cloudinary. So we're using Trino, really simple, really fun to enjoy. So we have Airflow DAG, which is scheduled on a cron-based. And what it does is for each table, we save the configurations in MySQL to understand how much data retention we want for that table, what time travel features, when to run delete orphan, and when to run rewrite manifest. And once we get the data, we actually let Trino use Trino procedures for Iceberg to run all these maintenance procedures. So now that we have compaction, ingestion, maintenance, and it's time to monitor and see what's going on with our table. So there are a few ways to monitor Iceberg tables. One is actually query the metadata table. So as you can see in the image, we're querying the snapshot table to understand how many added records we have, what was the operation. Was it replace is usually compaction, append is writing into the table, and we can extrapolate from that. Like if you look here, you can see in the red line, the average file size was 29 megabytes. So it's really, really small. And it's time to run compaction. So this table is really, really useful for you, because if you look under green line, the compaction process actually now ran compaction on the table, and it optimized it converted around 781 files into 40 files, and now the average file size is 500 megas. So you can just understand what you need to do only by querying a single metadata table. Another awesome thing that is provided by the Java API client in Iceberg is the metrics reporter API, which actually allows you to implement in Spark or Java a hook that once you run an operation in Spark, you can get a lot of metrics and send them wherever you want. So we're using Datadog, and we're sending all this data into Datadog. So you can see, for example, how many positional deletes were added, how many delete files, what's the overall size of our table, total bytes, and a lot of info, how many data files we have currently sitting on our table. And this is the final architecture currently with Cloudinary. So as I said, we ingest data from our CDN providers. We have Spark that does the ingestion and compaction. But now if you look at it, we don't have a single query engine to access the data. So now each team has the option to choose any query engine they want. So some, like data science, use Snowflake because they really love Snowflake. I don't know why. Data team, my team uses Trino for the main part. Ingestion, we're still a Spark workshop, so we love Spark. I also don't know why. And you get CS that are less technical. They use Athena for querying the, and since, so once we moved to this data lake architecture, there was one thing we noticed was now you have a different problem. Which query engine do I use? Huge problem. And we found out that a lot of users don't understand what they need to use, what query engine. So as you see in the image, we have a proxy engine, which now that you're in data lake, what we do for customers that don't know, like CS and other teams, BI, that don't know exactly what to do, we wrote a proxy engine that actually analyzes the query, tries to understand what is the approximate data that's going to be scanned, and it routes the query according to what we see would be the best fit for the query engine. So, and that really helped us because when we moved to data lake, the multi-query engine problem really creates a huge problem for your consumers that don't really understand, because in data warehouses you have one query engine and you just pick the size, and it doesn't always fit what you need. So benchmarks. So usually when I reach this point, I ask people, what do they think? What was the best query engine for running queries on the data lake? And each time I hear somebody say, and it's always biased, like somebody says Trino, somebody says Athena, somebody working in AWS. And usually I say, well, if you look at it now, once you reach data lake, there is no one query engine that rules them all, but you get an option to choose what's the best fit for your query. So what we did here at Cloudinary, we did a benchmark on queries, and we tested out a few engines, Amazon EMR Trino, Snowflake without Iceberg, Snowflake with Iceberg, Starburst, and Athena. What we did is we normalized the queries. So we took Amazon EMR, we ran it, and according to that result, we benchmarked all the other queries. So query one was a huge aggregation that runs on 10 terabytes of data. And what it does is it calculates for each customer the bandwidth it used for that 3 days of data. And what we saw is, so in cases of Athena and Starburst, they finished in half the time, which was really cool and amazing. But in other scenarios, like query 4, that was a huge benchmark. Some query engines didn't finish, and I'm not allowed to say which. But as you can see, Trino finished Trino and EMR finished really fast, almost faster than the others. But Starburst, in that case, finished in less than half the time. So it was really, really impressive to see all the features they support there. And now, so you have query duration normalized, but what about query cost. So now you look at cost, each query now, it's different, yeah. So of course, running EMR and Trino is the cheapest in cost, but it doesn't normalize the cost you need to pay your engineers to maintain those clusters. So it would be a lot higher. But if you look at it, now you can measure how much a query costs you according to the platform, the engine you're using. So if you look, like each query engine has a different pricing model. Athena is by data scanned, Snowflake, Starburst is by cluster size. And as you can see, if you take, for example, query number 1, you'll see that it costs 7 times more to run it on Athena than managing it by yourself. But that's a great thing. So you have to decide when you're moving to data lake and choosing query engine, what do you prefer, cost or performance? And it depends on your business use case. Questions?
I think Amit proved that he's not only a great expert on Iceberg and Spark and Trino and everything else, but also an amazing artist drawing snowy pictures.
It's all thanks to ChatGPT.
Oh, come on. Are you saying that wasn't you?
I only did the prompt and engineering. That's it.
All right, you're a great prompt engineer then. I'm sure we have some questions.
Yeah, I have 2 kind of related questions on the query routing aspect that you talked about.
Yeah.
So one, how do you smooth over like dialectical differences, for example, between Trino and Snowflake, if there are differences in functions supported or dialects? And then related question, how do you think about, like you showed kind of cost is not necessarily the same as performance. So like, what kind of heuristics do you use in the router to think about, it's a multi-objective optimization space, right?
Yeah. So regarding your first question, again, I need to refresher. What was the, again, sorry.
Differences in SQL dialect between Snowflake and Trino.
So difference in SQL, so we didn't support UDFs because it's not supported in it's hard to translate them between query engines. But we used an open source called SQLglot, which it has bugs, and I even opened a few and it was closed, fixed. But SQLglot is pretty good at translating between different query engines.
Also to note, on the translation layer, there's also another library that we're using in Trino for the Hive views called Coral. That's also an option. But the problem space of these different languages, basically the different languages, is massive, and there's always going to be problems.
Regarding your second question, how do we decide where to run? So essentially, it's a bit biased, but it makes sense. Usually, our customers are either teams inside the organization or outside. We use all kinds of statistics that currently reside in Iceberg to get an estimation of how data is going to be scanned. It's not precise, and it depends on the token being used. So when we see CS customer internal teams, we prefer to route it into some managed solution like Trino we manage, because running it on Snowflake can be very costly. And usually they just want some small report that doesn't require a lot of resources. But for customers, we'll route them to bigger clusters because we'll see that they need the answer immediately because they don't want to wait 5 minutes.
See, it's not a simple problem space. Nope. I think there's a question from the audience online.
Yep, we have a question from Tang Ma of how did you handle complex data structures like maps and arrays inside Snowflake with Iceberg?
So we didn't have a lot of complex data types when we get our data. What we did was most of our data is flattened. So we have a lot of simple columns, strings, numbers. Some we converted like JSON types. We converted into maps on Iceberg, but we didn't use any nested types because we're seeing it would cause a lot of problems when routing between query engines.
Another question about the proxy. Do you guys estimate the resource usage based on historical patterns or just based on the table metadata at runtime? So
yeah, we do save the query results and query planning to understand how much data was scanned. because it does help, because usually a lot of queries are, they're not new. Usually most queries are run the same query in different time ranges. So it's nice to save it. We use SQL Glut. We do parse the queries to understand what's like the parameters. So a lot of times you see like time is parameter in queries. Use that to understand later if that's the same thing. And if yes, then we can get a statistic of about how much data is going to be scanned.
Cool. I think we have one more question.
You used metadata tables for identifying which partition should be optimized. Do you have an automated tool that you use for doing that, or do you do it manually?
So,
and a follow-up question: Do you feel that you would find useful to have any other metadata tables from Iceberg that are not exposed by Intrino already?
So yeah. So currently we do our own optimizations. This is due to currently in Trino, you can't access all metadata through Trino. So for example, delete files, I don't think it's accessible through Trino, only Spark. And that was a key component because we needed to understand how many deletes do we have on a certain partition. Because if we have a lot, then we need to run the compaction process. So we actually wrote our own infrastructure to pull that info out and do the optimizations. But if you look at it, I think Iceberg currently has about around 9-10 metadata tables that should be accessible by every query engine, because it's like gold. It can help you understand what's going on with your table.
Awesome.
Last question.
Hi, Amit. Thanks for the presentation, very detailed. So just out of curiosity, in the last slide, why didn't you put the cost of the query for Athena?
What again?
If you go back to the last slide, like, why was the query, the cost for Athena missed?
Not sure.
Or did I miss something? Yeah. The query for Athena.
So why? So essentially, we decided not to run Athena on that query for a few reasons. One, it didn't finish. But when you look at it, also the query, so Athena, the pricing model is you pay for data scanned. And that query ran on, I think, more than 20 terabytes of data. So that would be a really, really expensive query. So we decided not to run it.
All right, awesome. Thank you so much again
Thank
for
you.
joining us today.